Hey everyone, and welcome to this explainer. Today, we're diving straight into the complex chemical and biological recipes that transform raw rock into the structured soils right beneath our feet. We usually look down at the ground and just think, oh, it's just dirt, right? Well, actually, underneath the surface, there is this incredible, highly dynamic world of chemical reactions and biological activity going on. So today, we're relying strictly on the science of soil formation to decode the Earth's pedogenic processes. Let's get into it.
Here is our quick roadmap for today. We'll start with the fundamentals of soil formation, then move into humification and translocation processes. After that, we'll cover zonal processes and climate's impact, followed by tropical laterites and arid salinization. Then we'll look at the sequence of salty soils and wrap up with pedoturbation, or the mixing of the soil.
All right, let's kick things off with Section 1, the fundamentals of soil formation, building the basic blocks of the Earth.
To really understand our landscapes, we have to first look at the invisible forces acting upon raw geological parent material. You see, geological weathering sets the stage by breaking down rock, but it's what happens next that actually creates the soil. Pedogenic processes are the complex, dynamic, chemical, and biological reactions that change this weathered rock into mature soil with distinct layers, which we call horizons. And these processes are operating simultaneously. Sometimes one process will completely counteract another, or two might actually team up to achieve the exact same result. And get this, here's a fascinating fact directly from our source material. While all pedogenic factors contribute to soil development, no single soil is influenced by every pedogenic process. Instead, each soil is formed by a unique combination of additions, losses, transformations, and translocations, which is just a fancy way of saying the physical movement of materials.
Moving right along to Section 2, humification and translocation processes, the movement of organic and mineral matter. So, before we zoom out to look at macroclimates, we need to understand how matter breaks down and physically moves within the soil profile. Think of these processes as the engines that build the soil's internal architecture. The creation of humus is an intricate two-phased biological dance involving bacteria, fungi, earthworms, and termites. First up, we have mineralization. This is where soil microorganisms biochemically break down dead plant tissues into simple, soluble organic substances, mineral compounds, and gases like carbon dioxide. Once that breakdown is done, phase 2 kicks in, humification. This is where those soluble organic substances actually regroup themselves into large molecules through polymerization, becoming poorly soluble. They form the major part of soil humus, which is absolutely vital because it provides the essential sites for retaining chemical cations. Now, it's super helpful to visualize this next process as a continuous downward conveyor belt driven by water. Eluviation, with an E, simply means washing out. It encompasses the mobilization and removal of mobile constituents, like clay and iron oxides, from the upper layers by percolating water. When this is just the mechanical movement of clay without any chemical alteration, it's called lessivage. But, what goes down must stop somewhere, right? That brings us to illuviation, with an I. This is the washing in or deposition of those exact same materials into the lower layers. This creates stabilized zones, typically called the alluvial B horizon. So simply put, eluviation strips the top layer and illuviation builds up the bottom layer. It is absolutely wild how perfectly this data maps the relationship between a region's rainfall and exactly how deep elements are leached into the ground. If we look at elemental mobility, calcium and sodium are highly mobile, while aluminum is the least mobile. The real-world effect of this leaching is brilliantly illustrated by checking out where calcium carbonate accumulates. In a hot, arid zone where you have very little water percolation, that calcium carbonate stays super shallow, less than 50 centimeters deep. In a semi-arid zone, it washes down to between 100 and 150 centimeters. But in a subhumid zone with plenty of rain, boom, it gets pushed deeper than 150 centimeters. The climate literally dictates the depth. Okay, Section 3, zonal processes, climate's impact, how macroclimates shape the ground. With the basic movement understood, let's look at a large-scale zonal process called podzolisation. This term actually comes from the Russian words pod, meaning under, and zola, meaning ash-like. It's an intense leaching process that happens in cool, humid climates, often up at high altitudes. It absolutely thrives under acid-loving vegetation, think pine trees or heath. In this calcium-free environment, where the pH drops below 5.0, fungi completely dominate the decomposition process.
Soluble organic acids react with sesquioxides and clays, washing them right out of the upper soil. And what's left behind? A highly acidic, ash-like, bleached horizon that has been totally stripped of its basic nutrients. Which brings us to Section 4, Tropical Laterites and Arid Salinization, Extreme Heat and its Opposing Pedogenic Results. While cold forests bleach the soil, tropical heat and arid deserts trigger entirely different chemical reactions. In stark contrast to podzolisation, we have laterization. This happens in warm, humid tropical climates. We're talking 25 degrees Celsius and massive rainfall, up to 2,500 millimeters, right under the tropical rainforests. Here, organic matter decomposes incredibly fast, and when you combine this intense heat and leaching with basic parent materials, something fascinating happens: desilication. The alkaline environment actually makes silica soluble, so the silica is just leached away. Meanwhile, iron and aluminum oxides are left behind, coating the remaining particles in these really characteristic red and gray colors. So here is the crucial takeaway. This intense tropical weathering strips away the silica and leaves behind a non-plastic, non-cohesive soil. It is massively impregnated with iron and aluminum, sometimes making up 70 to 80% of the total mass. Because of that, when it dries, it literally cements into a surface as hard as a brick. The source material points out that the term laterite itself actually comes from the word latter, which literally means brick or tile. These soils, like the ones you'd find in the Malabar Hills of Kerala, have super low fertility and high phosphorus fixation, making them mostly suitable just for plantation crops. All right, shifting gears to Section 5, the sequence of salty soils, intrazonal processes, and local terrain. We are now shifting from climate-driven zonal soils to intrazonal processes. This is where local topography, depressions in the land, and poor drainage take total control of the soil's destiny. Let's start with a process intimately tied to waterlogging: glaciation. Gley literally translates to blue, gray, or green clay. This happens in lower topographic positions where there is a total lack of aeration. Because the drainage is so poor, the environment goes anaerobic. Microorganisms are forced to respire anaerobically, and in doing so, they biologically reduce iron compounds into soluble ferrous forms. This chemical reduction radically transforms the soil's appearance, turning it these striking shades of blue and green right above the parent material. Now, let's see how local terrain builds a continuous sequence in arid regions with shallow, brackish groundwater. It starts with Step 1, salinization. Capillary action pulls groundwater up, leaving salts behind as the water evaporates, but the exchangeable sodium percentage, or ESP, remains below 15%. Now, if carbonates predominate, calcium and magnesium precipitate out, allowing sodium to take over the clay exchange complex. That triggers Step 2, alkalization, where sodium pushes the ESP above 15% and spikes the pH over 8.5. Finally, we have dealkalization, which is the removal of that sodium from the exchange sites by introducing calcium and improving the drainage. And this whole sequence gives us a massive visual contrast in these salty soils. During basic salinization, when capillary water evaporates at the surface, it simply leaves behind a white crust of sulfates and chlorides. We call these white alkali soils. But when the soil transitions into alkalization, that severe sodium saturation spikes the pH. And this high pH actively dissolves the soil's humus. That dissolved organic matter moves upward with the capillary water and coats the soil in a dark color. We call these black alkali soils, and their highly dispersed clay makes them incredibly hard, totally impermeable, and honestly terrible for aeration. And finally, Section 6, pedoturbulation, mixing the soil, the physical churning of the earth. We've talked a lot about water vertically leaching chemicals down or capillary action pulling salts up, but mechanical forces are constantly mixing those carefully layered horizons too. This physical mixing is known as pedoturbation, and it actively offsets the distinct horizon layers we've been discussing. It comes in a few forms. Faunal pedoturbation is driven by animals. We're talking ants, earthworms, rodents, and human activity too. Floral pedoturbation happens through plant mechanics, like when a huge tree tips over and completely rips up the ground, forming pits and mounds. Lastly, we have argilopedoturbation. This is the heavy lifting done by the soil itself, specifically through the extreme swell and shrink action of specific clays, like deep black cotton soil. So whether it's an earthworm burrowing or intense tropical heat baking out silica to form a brick like laterite, the ground we walk on is in a constant, relentless state of transformation. Understanding that soil isn't just static dirt, but an active, ongoing battleground of these dynamic pedogenic processes, well, it completely changes how we view the landscapes around us. So, considering the local climate, the drainage pressures, and the physical churning happening in your specific environment right now, which complex pedogenic process is operating right beneath your feet? Keep exploring, focused learners, and we'll see you in the next explainer.